I have a question for you. We haven't set foot on Jupiter, Saturn, Uranus, or Neptune yet, or on any celestial body billions of light years away from us. So how do we know, for example, that the atmospheres of those planets contain hydrogen and helium, or that Jupiter and Saturn have liquid metallic forms? We haven't gone there, right? How do we know all this about the universe, about everything happening around us? Actually, there's one answer to all of it. The source of all this knowledge: light. Yes, we've talked about this before, and we'll dive deeper, especially when discussing electromagnetism from the starting point of quantum mechanics. But what is light really? How is it formed? We haven't covered that yet. You can think of this as a new beginning video on quantum physics. It'll lay everything down at the foundation, equipping us better for our quantum journey ahead. A single source with all the info you'll need. You know so far science. I want everything to be understood. A quick warning before we start. This will be a pretty information-packed video. You might want to pause at times to take notes. We'll cover quantum physics, spectroscopy, the Doppler effect, bits from different fields. Then we'll tie it all together. For centuries, through experiments, debates, and research, we concluded light is a wave. With Maxwell's contributions, we answered, what is light? Light is an electromagnetic wave. Not wrong at all. Let's start with that definition. When we say light is a wave, what are we talking about? Yes, light is energy, an electromagnetic wave, so it moves in waves, like ocean waves. But light waves are caused by electric and magnetic fields. Light is the intertwined state of these two fields. That's why light's other name is electromagnetic radiation. Let's visualize it. Like ocean waves, imagine swimming between them. One wave comes, you rise, another follows. You go up and down. The region between these two waves is called wavelength, a term we'll use a lot with light, wavelength. And light's most important property is this wavelength, because light's energy depends on the length of this wavelength. Light with a shorter wavelength has higher energy, while longer wavelength light has lower energy. We observe this energy all the time, through colors. If you say you see something purple, you're actually talking about short wavelength light reaching your eyes. Red has a longer wavelength, so we can easily say red's energy is lower than purple's. All the other colors we see have their wavelengths too. These different wavelengths of colors are called the spectrum. But the colors we can see are just a tiny sliver of this massive wave. Our eyes are tuned to the strongest light from the sun. That's how we see. If the wavelength is a bit shorter than what we can see, we call it ultraviolet. Shorter still, X-rays. The shortest wavelengths are gamma rays, or if it's a bit longer than visible, infrared. Longer, microwaves. The longest, radio waves. These wavelengths aren't sharply divided, by the way, but together we call the whole thing the electromagnetic spectrum. And we said wavelength is inversely proportional to energy, so gamma rays have the highest energy, radio waves the lowest. Step back and look at the full spectrum. You'll see our visible light is super limited. For the parts we can't see, we didn't just sit idle. We built countless telescopes. They opened doors to unseen worlds. But one question remains. Where does this light come from? What's the source? How does it emerge? Time to talk briefly about matter. One of matter's basic properties: heat it and its energy increases. Matter doesn't like this excited state. It does everything to return to its original standard energy level. Light is a form of energy too, so it ejects excess energy as light, and in doing so, emits light. How does it emit different types of light? What decides that? Another property of matter comes in. A hot object's emitted light has high energy, so short wavelength. Cooler objects emit lower energy light. Try heating an iron rod. It glows red first, then orange, hotter, yellow. Even hotter, the wavelength and color shift to blue. Higher energy means bluer. Astronomers' perception differs from ours. We say cold is blue, hot is red. But science doesn't care. Red is cooler than blue. Looking out into space, we also see low-density light emitters like gas clouds. To understand them, we'd normally need to examine their atoms under a microscope, but we don't. Why? Let's dip back into the quantum world. We need to peek into this bizarre realm. Time to talk atoms. We know what atoms are made of: neutrons, protons, electrons. Protons positive, electrons negative, neutrons neutral, as the name says. Neutrons and protons in the nucleus. Electrons, you know. Atom images show electrons orbiting the nucleus, but their exact position is fuzzy, somewhere around. Everywhere at once, actually. We'll get to that. The key: electrons have very limited, precise spots they can occupy around the nucleus, tied to their energy. Positions are strictly either or, no in between. Like staircases, electrons on step 1 or 2 can't be midway. Climbing stairs, each step costs energy. Low energy, you stay on one step. Same for electrons. Give enough energy, they jump positions instantly. Remember quantum leaps? But they always try to return. To do so, they shed energy. How? Light. Shine light on an atom, electrons gain energy and leap. Returning, they emit it as photons. Light emerges. Doesn't have to be one step. Enough energy means 2 or 3, but no halfway, remember. That's what Max Planck discovered. Light acting particle-like. Quantum physics' origin. Also, energy equals wavelength, we said. Colors correspond too. All the same thing. An electron jumping down emits a very specific color based on position. Different atoms emit different colors for this reason. That's the universe's foundation. We identify a body's composition from billions of light years away. Different atoms emit distinct colors, measure the light, know what's there without visiting. Amazing, right? How do we do this? Measure the light. Spectroscopy. Studying light-matter interaction. With a device called a spectrometer, it shows exactly which wavelength a color is. That viral dress, blue or gold? Spectrometer said both. No one's wrong. Camera, ambient light, angle, biology, all factor in. Everyone's right. Both are true. Anyway, spectrometers reveal wavelengths, so we distinguish helium from hydrogen light. Attach one to a telescope, you see stars' compositions. That's how we learn the universe. Back to the start. Stars and gas clouds are mostly hydrogen, some helium, trace heavy elements. Jupiter's atmosphere has methane, Venus carbon dioxide. Everything has its signature. Spectroscopy lets us taste it. Not just that, we learn speed, rotation direction, magnetic fields and strength, mass, density. One last thing, Doppler effect. That motorcycle roaring past? Sound has wavelengths too. Peaks shortest up close, stretches as it leaves. Same for light. Approaching, wavelength shortens, blue shift. Receding, lengthens, red shift. Applied to spectrum, know if it's approaching or receding. Why it matters? We learn the universe is expanding. And, as always, until next time, glad you exist. Much love.